uh, gravitational force. Okay, now what we do have, we have two masses, the mass m1 and mass m2. So between these two masses there is a force of attraction. Okay, we know that this force of attraction is directly proportional to the product of the masses of these two objects, meaning that this F is proportional to m1 times m2. The second thing, that it is inversely proportional to the square of the distance between these two objects. For example, r is the distance between these two objects. Then we can say this F is inversely proportional to r square. Now we combine both of these forces, these equations, and we find that F is proportional to m1 times m2 divided by r. That means F is equal to G, the gravitational constant, times m1 m2 divided by r. This, yes, r square, yes, this is the r square, because we have here r square. Yeah, you are right. So this is r square. So here this G is a universal constant with the value of 6.627, about 10 raised to power minus 11 Newton meter square per kilogram square. Okay, this is actually the our force. Now you can actually ask this question, that which object is actually applying this force. This object number 1 is attracting m number 2, or other way around. In fact, it is on both ways. M1 is applying this force on M2, and M2 is attracting M1 with the same force here. Okay, now exactly, they attract each other. Now you can raise question that which one will move toward the other. And here in this, actually our example, both masses are the almost, actually let's say presume that both are the same. So in that case, we know that according to Newton's second law of motion, that when a force F applied on a mass m, it will gain acceleration, isn't it? So if this force is significant on this object m2 applied by m1, and its mass is also, you can say, comparable to the other mass, then it will actually feel the same force, meaning that both objects may feel the same force. If we presume that our one mass is a very, very big mass, like the mass of Earth. Okay, and that exactly true. So then in that case, we can presume that this object is our small mass. So if mass is smaller, we know that our acceleration is inversely proportional to the mass, meaning that the force between these two objects is the same actually on each other. What the acceleration of a smaller mass will be bigger than the acceleration of the bigger mass. Okay, so that is why in this case the smaller mass will move towards the bigger mass. Okay, and now you can say that actually this force, which is giving the acceleration, is coming because of this force, which is the gravitational force. Now we can say that ma is equal to capital G, and now one mass is the small m, other mass is the mass of Earth, and then divided by r square. Okay, and here our assumption is that small m is close to the surface, close to the surface. Okay, close to the surface of the earth. Okay, if this is the situation, then we can say the distance between the earth and this small object is almost the radius of the earth. Okay, and here a, which is the acceleration, this acceleration will be because of the force of gravity. So then we can say that this is g, this is g. And here in this actually equation you can see this small m and this small m, they will cancel with each other. Okay, and we left with the value of g is equal to capital G, which is a gravitational constant, universal constant, mass of earth divided by the radius of earth and its square. Now you can see that this gravity, the value of the strength of the gravity, the value of strength of the gravity, where when we are close to the surface of earth, is mainly depending on the parameters of the earth. What parameters of earth? Mass of the earth and radius of the earth. Okay, understand? So let's call it the G naught. So this is our reference value, which we know that it is 9.8 Newton per kilogram square. Okay, sorry, not a square. So this is not square. Okay, Newton per kilogram. Okay, now here our assumption, again let me remind you, was that we are close to the surface of earth. Okay, now we move toward our question, that what will happen if we will go away from earth. Okay, if we will go away, we are not close to the surface anymore. Okay, meaning that the distance, the height h now is significant. Okay, it's a quite much. So in that case we will say that our situation